On 19th of December 2025, 3i Atlas reaches its closest point to Earth, yet it remains very far away, roughly 1.8 astronomical units, about 270 million kilometers, nearly twice the average Earth-Sun distance, and more than 700 times the Earth-Moon distance. In other words, it is a scientific opportunity, not a hazard. The name itself is a clue to why astronomers care. 3i marks the third confirmed interstellar object seen passing through the solar system, and Atlas credits the Asteroid Terrestrial Impact Last Alert System survey that first reported it on 1st July 2025. Soon after, additional astrometry extended the observation arc and locked in an unbound hyperbolic trajectory, meaning the object came from outside the Sun's gravitational family, and, after its swing through our neighborhood, it will leave and never return on any human timescale. NASA's own summaries emphasize a simple, testable storyline. 3i Atlas is an active comet with a solid, icy nucleus surrounded by a coma, and its activity is driven by solar heating that turns ice into gas, lifting dust and shaping the visible tails. That cometary physics, plus small non-gravitational accelerations consistent with outgassing, is the mainstream explanation for the subtle course corrections that sometimes look unnatural when reduced to short social media clips. The biggest reason 3i Atlas feels dramatic is that it arrived at exactly the wrong time for calm interpretation. The object was discovered while it was still faint. Then it quickly became the center of a crowded observational campaign involving ground-based observatories and a surprising set of spacecraft that happened to be well-placed. That created a modern pattern where early data drips out as thumbnails, press images, or instrument snapshots, while the full calibrated datasets appear later in archives, an innocent gap that rumor communities often treat as a plot device. That gap has produced its own small micro-mysteries. Some watchers say a handful of frames or thumbnail sets briefly appeared in a public gallery, and then were replaced by reprocessed versions. Others point to tiny shifts in metadata between downloads. None of that is evidence of a cover-up. Reprocessing and cache syncs are routine, but it does create a forensic question that keeps people talking: what changed, why, and who decides which version becomes the canonical one. Even before today's closest approach to Earth, the comet had already provided unusually intimate views for a visitor from another star system. For example, NASA's Mars Reconnaissance Orbiter photographed 3i Atlas on 6 October 2025 from about 30 million kilometers away, one of the closest looks any spacecraft or Earth-based telescope was expected to obtain, and other Mars missions and heliophysics missions also contributed images and measurements that let scientists compare how the coma and tails respond to different solar wind conditions and viewing angles. NASA has also showcased a multiple lenses approach, ultraviolet images tracing hydrogen and other escaping atoms, wide-field heliophysics observations that catch the comet as a moving point with a compact tail, and high-resolution snapshots that reveal structure within the coma, each instrument sensitive to different physics, each one adding a piece to the puzzle of how an interstellar comet behaves when it encounters a new star for the first time in billions of years. ESA reports a similarly broad campaign, noting that 3i Atlas has been observed by a mix of ground-based telescopes and space observatories, including Hubble, the James Webb Space Telescope, XMM Newton, and XRISM. This matters because the comet's light is not just pretty, it is a chemical fingerprint, and different wavelengths reveal different ingredients: dust, water-related fragments, carbon-bearing gases, and energetic interactions between cometary gas and the solar wind. Today's closest approach geometry is particularly helpful because it sharpens what observers can measure. The apparent position against background stars can be pinned down precisely. The brightness can be tracked over hours to infer rotation or repeating outbursts, and the orientation of tails can be compared with models of dust dynamics, plasma interactions, and line-of-sight effects. NASA's sky-watching guidance stresses that a decent telescope is required, but it also points out the simple viewing logic. pre-dawn, looking east to northeast, with the comet appearing in the vicinity of Leo and near Regulus for many observers. From a scientific standpoint, the most headline-worthy number is not the Earth distance, but the comet's interstellar speed. An object arriving on a hyperbolic trajectory is not looping around the Sun the way a long-period comet does. It is passing through, carrying information from a different stellar nursery. That is why researchers have been racing to estimate its size and to constrain its composition with spectroscopy and thermal models. A quieter but equally important story is how the community manages uncertainty. Early in an object's discovery, limited data can make trajectories look more dramatic than they are. That is why the Minor Planet Center's electronic circulars and the steady cadence of orbit updates matter so much. As the arc grows, the solutions converge, and in this case, the official consensus is stable. 3i Atlas is not on a collision course. It is not even close in astronomical terms, and the closest approach headline is simply a milestone on a safe path. So where do the strange vibes come from? Partly from genuine cometary oddities that are easy to misread. Anti-tails and sunward-pointing features can appear when dust lies in the comet's orbital plane, and the viewing geometry makes that dust look like it is pointing the wrong way. Brightness changes can be driven by jets turning on and off, or by the nucleus rotating so that active regions come in and out of sunlight, and a shift in a measured periodicity can happen when the coma changes shape, when different instruments emphasize different gases, or when the rotation state is complex rather than a simple spin. But the other source of strange vibes is cultural. 3i Atlas went viral. It became a canvas where people project anxieties about secrecy, geopolitics, and technology. Some online threads claim that data disappeared, or that certain images were replaced, or that access was cut off, and those claims spread quickly because they are hard to disprove from the outside. A related rumor pattern is technical rather than cinematic. Short outages, 404 errors during archive mirrors, rate limits that look like access cuts, and the slow replacement of provisional products with calibrated ones. In practice, those are ordinary workflows. In rumor spaces, the same symptoms are read as intent. That ambiguity, normal operations that can be misread, keeps the story alive without needing any hard proof either way. Importantly, none of that by itself demonstrates wrongdoing. Archives are updated, calibrations take time, and mission teams routinely embargo raw frames until they can be properly interpreted. Yet the timing of updates can look suspicious to anyone primed to expect censorship. To keep speculation anchored, start with what is verifiable. Multiple agencies openly state that the comet is far from Earth on 19th of December 2025. They publicly publish ephemerides and encourage observation, and they describe the object as an interstellar comet with a coma and tails, not as a solid craft. Those are the facts you can check in official FAQ pages, skywatching guides, and mission updates. Now layer interpretation on top of those facts. Because the object is interstellar, it is reasonable to ask whether its chemistry differs from local comets. Because it is faint and fast, it is reasonable to ask how reliable early light curves are. Because spacecraft observations come from instruments built for other targets, it is reasonable to ask whether odd artifacts or processing choices might look like anomalies to non-specialists. And because it is the third interstellar visitor ever confirmed, it is reasonable to expect surprises that do not fit our small sample of experience. Only after that foundation does the rumor layer become interesting, not as a conclusion, but as a question. Some commentators suggest that a subset of reported anomalies, unusual tail geometry, unexpectedly strong signals in specific spectral lines, or a rotation axis that appears to prefer a sunward orientation, could hint at non-standard physics. A few go further and ask whether a technological explanation is even conceivable. The honest way to write that is not, "It is a spaceship," but if the measurements persist after calibration and independent replication, what natural mechanisms could produce them, and what would a genuinely artificial mechanism need to look like to be distinguishable? In this style of narrative, the strongest rhetorical fuel is the gap between what can be measured and what can be explained quickly. For example, if an instrument team releases a composite image showing a wide hydrogen halo, viewers may wonder why the halo looks asymmetrical. The mundane explanation is that solar wind and radiation pressure sculpt escaping atoms, but a rumor-minded reader might ask whether the asymmetry could reflect directed activity. Both can be written in the same sentence if you keep your verbs cautious. The asymmetry is consistent with solar wind shaping, although some observers argue it could also be produced by a preferred jet direction. Another believable mystery is time. The closest approach is a single date, but the most valuable data come from weeks on either side. When viewing angles and solar conditions change, that means announcements come in waves, and silence between waves is normal. Still, the absence of immediate explanations can tempt people to fill the vacuum with intent. A careful writer can acknowledge the vacuum without endorsing the intent. Why certain datasets are still pending is not publicly detailed, but delayed releases are common when calibration and cross-instrument comparisons are required. A third lever is institutional diversity. NASA, ESA, university observatories, and independent amateurs all contribute, and their results appear in different formats. This diversity makes a coordinated cover-up harder in practice, yet it also makes communication messy. Rumor narratives exploit messy communication by treating normal disagreement as a fight and normal caution as fear. A more responsible suspense narrative treats disagreement as a feature of science. Teams debate because the object is unusual and the sample is small. Extraordinary interpretations remain speculative until they survive independent tests. So, what is actually new right now, on the day of closest approach? First, the geometry is now locked, not predicted. The comet has, in real time, reached the minimum Earth distance that was calculated weeks ago. Second, the campaign is at peak intensity because the object is already heading outbound and fading. Third, additional spacecraft snapshots and heliophysics measurements gathered in the run-up, particularly those that probe ultraviolet and wide-field heliospheric structure, are being combined to tie visible changes in the coma to invisible changes in particle environments. This context is crucial for separating a real anomaly from a natural cometary reaction to solar wind conditions. Fourth, the public conversation has also hit peak intensity, and that is where the 3-eye atlas myth grows. Posts highlight a single frame or a single parameter and treat it as definitive. Yet the real story is statistical and multi-epoch. If a periodic heartbeat is reported by some observers, the scientific response is not dismissal, but replication. Do multiple telescopes see it in multiple bands over multiple nights? And does it correlate with rotation models or outgassing jets? Only then does a pattern become data, and only after that does it become a physical explanation. Fifth, and maybe most important for a grounded suspense text, official sources keep repeating the same constraint. The comet is safe, the value is scientific, and the remaining time to observe it well is limited. That simple repetition is exactly what conspiracy storytelling tries to invert. They keep saying it's safe, therefore it isn't. But repetition can also be interpreted as boring sincerity. Both readings exist, and a careful writer can present them as competing lenses rather than as a verdict. If you want a conspiracy-flavored tone that still respects reality, aim your mystery at interpretation, not at danger. The most plausible intrigue is not impact, but meaning. What does its chemistry say about its parent system? How old might it be? How does interstellar dust differ from solar system dust? And what can we learn about planet formation beyond our star? In that frame, even the wildest internet claims become, at most, metaphors for the deeper truth that we are looking at something genuinely foreign. And if you want that tone to feel real, you keep the door open in both directions. It could turn out that 3-eye Atlas is a fairly typical comet from a different system, and that the weirdness was mostly geometry, small number statistics, and the psychology of viral attention. Or it could turn out that it contains a compositional surprise that forces new models of icy bodies. What is unlikely, based on the public evidence and the physics of comets, is that the object is a controlled vehicle, but even that extreme claim can be handled responsibly by framing it as an unsupported hypothesis and by emphasizing what would count as disproof. In the end, the most honest closing line is not a punchy accusation, but an invitation to evidence. Watch how the datasets evolve over the next weeks. Notice which anomalies persist under independent analysis, and notice which ones fade when geometry and calibration are accounted for. Coincidences do happen in astronomy, but so do genuine surprises. Whether 3i Atlas becomes a footnote, a benchmark, or a case study in how the internet rewrites science in real time, the answer will come from the same place it always comes from: repeatable observations, transparent methods, and a willingness to say, "We don't know yet," without turning that uncertainty into certainty. A few dates anchor the entire arc. Discovery on 1st July 2025, a particularly favorable spacecraft view in early October 2025 as it passed near Mars's orbit. Perihelion near 30th October 2025 at about 1.4 AU from the Sun, just inside Mars's orbital distance. And then the Earth distance minimum on 19th December 2025. After that, the comet continues outward, crossing the region of the giant planets over the coming months, with NASA noting that it will pass the orbit of Jupiter in spring 2026, and then keep going, slowly dimming until it becomes another anonymous speck for deep surveys. Those milestones matter because they explain why certain images appear when they do. The Mars flyby geometry let a Mars orbiter take a high-resolution look. The perihelion period increased activity, but also pushed the comet closer to the Sun's glare for Earth-based observers. And the December geometry moved it into pre-dawn skies for many latitudes, near the constellation Leo, where observers could locate it relative to Regulus if they had dark skies and a telescope. Official skywatching notes are blunt about visibility. Even at its best, it is not a naked-eye object. It is a telescopic target, and not an easy one. Guidance from NASA suggests a scope on the order of 30 cm aperture for a reasonable chance, plus patience, good tracking, and an understanding that what you see visually will be subtler than the colorful images processed from long exposures. Because of that gap between what a backyard telescope reveals and what a space telescope can extract, the story naturally splits into two parallel experiences. For the public, it is a faint smudge moving night to night. For scientists, it is a data cube, a spectrum, a time series. And it is in the mismatch between those two experiences that misinterpretations flourish. People compare a filtered, contrast-stretched composite from an ultraviolet instrument to a noisy smartphone image and conclude that something is being hidden, when in reality they are looking at different physics. A grounded mystery text can also lean into how ephemerides are produced. Positions are derived from astrometry against background stars, fed into orbit determination software, and updated as the object is tracked. NASA's JPL publishes tools like Horizons that can output observer tables, distances, and velocities. The important point is that a close approach number is not a guess pulled from a headline. It is a computable consequence of the best fit orbit and its uncertainties, and when multiple independent groups converge on the same result, confidence rises. If you want to write suspense without cheating, describe uncertainty in the way scientists actually experience it, as a narrowing funnel. Early on, the range of possible nucleus sizes is wide because the coma contaminates brightness estimates. Later, when the object fades and the coma thins, constraints improve. Similarly, early claims about composition can swing wildly depending on which emission lines are present and how the instrument background is handled. Later, multiple observatories either confirm or fail to confirm those lines. This is where the phrase, "some researchers think," can be used responsibly. It is fair to say that some researchers interpret particular spectral hints as evidence for unusual abundances, while others attribute the same hints to measurement artifacts or to a specific outgassing regime. It is not fair to state that a controversial interpretation is the official conclusion. The tone stays credible when you keep the competing explanations in view and make room for ordinary physics to be the answer. In fact, one of the most interesting aspects of 3I Atlas is how ordinary physics can produce extraordinary-looking behavior. Non-gravitational acceleration is a known effect in comets because jets act like tiny thrusters. Orientation matters because jets are not symmetric. And if a jet is collimated and persistent over part of a rotation, the comet can show a small but measurable deviation from a purely gravitational orbit, which, when plotted without context, can resemble steering. There is also a well-understood reason some comets show multiple tails and color shifts. Ion tails glow in ways that depend on solar wind conditions, while dust tails reflect sunlight and depend on grain size. When conditions change, the relative prominence of tails can change. Add a sunward-pointing dust feature created by geometry, and you have a perfect recipe for "it's pointing the wrong way" narratives that feel compelling precisely because they seem to contradict a simple cartoon model of a comet. That is why the best conspiracy-style writing in astronomy often focuses on the sociology of information rather than the physics of objects. Who releases what, when, and how? What gets amplified? What gets misunderstood? And how uncertainty is misread as concealment. You can write, truthfully, that some datasets are released first as curated images, while raw telemetry takes longer. You can write, truthfully, that mission constraints sometimes force teams to downlink low-resolution previews, and you can let readers decide whether that normal workflow feels reassuring or suspicious without claiming evidence of a plot. If you choose to include anonymous sources as a narrative device, keep them bounded. An anonymous observer can say, "The field was crowded, and the comet was hard to pick out near dense star fields," a plausible observational challenge, without inventing claims about secret briefings or classified payloads. Realism comes from mundane constraints, not from cinematic revelations. The more you ground the narrative in real constraints, solar elongation angles, instrument saturation, tracking rates, background subtraction, the need for repeated observations, the more any speculative "what if" will feel anchored. Paradoxically, the most believable conspiracy atmosphere is created by accurate details that have nothing to do with conspiracies. You can also remind readers that interstellar objects are rare, but not unprecedented. Oumuamua and Tui Borisov are the previous confirmed cases, and both generated their own debates about odd acceleration, shapes, and the limits of our models. 3I Atlas inherits that cultural memory, so every small oddity is instantly compared to Oumuamua, even when the object is, by official descriptions, a visibly active comet rather than a dry, asteroid-like body. Finally, there is a subtle narrative twist that stays true. The closest approach to Earth is a headline, but the more scientifically meaningful close approach may have been elsewhere. The October spacecraft imaging distance near Mars was far closer than the December Earth distance. That means the most detailed morphological evidence may come from a date that casual readers overlook, in a suspense text that becomes a quiet hook. The sharpest eyes saw it earlier from another planet's orbit, and we are only now catching up. And that, too, can be read two ways. Either it is simply the messy reality of many teams publishing at different cadences, or it is the kind of coordination gap that makes people suspect coordination. The more responsible move is to treat that tension as a question you can track by watching version histories, calibration notes, and independent reductions, rather than as a verdict. By framing the story this way, you can keep a thriller tone while still honoring the boundaries of evidence. The official record says the comet is safe and cometary. The data campaign says it is scientifically valuable, and the internet says it is emotionally irresistible. The tension comes from the collision of those three truths, not from fabricating dangers that do not exist. As the post-19 December analyses begin to circulate, watch for the telltale markers of maturity, papers that state their uncertainties, independent teams that reach similar conclusions, and instrument teams that publish calibration details. If a supposed anomaly survives that process, it will become more interesting, not less. If it evaporates, it will still teach a lesson about how easily the eye and the algorithm can be fooled when we are hungry for patterns. Until then, the most accurate way to end a mystery about 3I Atlas is with an open, evidence-based question. Is the comet merely a familiar kind of icy body from a different stellar birthplace, or does it contain chemical and physical signatures that will force new models of interstellar debris and planet formation? Everything else, plots, visitors, messages, may be entertaining, but it remains speculation, and the cosmos has a habit of being both stranger and simpler than our stories at the same time.